These are important ones. Okay. Now, where do we have applications of this? Actually, this has a lot of applications in real life. For example, I'll tell you one thing which used to be part of syllabus, but not anymore. There is something called resonance. Resonance. It is deleted now, but still you will need that in class 12. Resonance. I can tell you, listen to me, please. Imagine you are giving an external frequency. Listen. There is a frequency that please. There is a frequency that, listen. There is a frequency that every vibrator would love to vibrate at. For example, if I strike my body, if I strike my body vibrates at say 70 hertz, which means it vibrates 70 times in a second. All right. Or if I pluck a guitar string, the string vibrates say 100 times in a second. Okay. So even if I strike the board vibrates say 40 times in a second. That is called its natural frequency. Natural frequency. Everyone has natural frequency. Okay. If you give the same natural frequency from outside, there will be vigorous vibrations. That is called resonance. The condition is called resonance. That is what, when there is an earthquake, seismic waves are produced. Earthquake waves are produced. Okay. Earthquake waves. These earthquake waves have a frequency. Imagine the building of Excel has the same frequency as the seismic wave. This building will vibrate vigorously. It will eventually collapse. There is a very famous photograph of an earthquake. If I remember, it is in Mexico. And all the buildings collapsed where one building alone stood up because that building did not have resonance. Because its frequency did not match the frequency of the seismic wave, earthquake wave. I'll tell you a simple example so that you can understand easily. I can break that window glass just by singing. Right, singing. Have you heard of opera singing? Opera singing? Singing at very high frequency. So when you sing, your frequency, by chance, if it matches the frequency of glass, it will start vibrating. It will eventually, when the vibrations become vigorous, it will eventually break. All right, it will shatter. Okay. So basically, this is the point. We have the same concept in class 12 also, resonance. The external frequency, the frequency you give is equal to its natural frequency. We have a condition called resonance. And in 1940, in US, a bridge in a place called Tacoma. You must have heard of it, Tacoma Bridge. And 6 months into construction, the bridge collapsed. 6 months. 6 months in, because it was a suspension bridge. And that was a very strong windy region. And then wind used to blow at very high frequencies. At one particular point of time, frequency of wind matched the frequency of the bridge. Frequency of wind, the wind blows how many times per second? That matched the frequency of oscillations of bridge. At that point of time, there was collapse. The bridge collapsed. 6 months after construction, afterwards, they take precautions. Suspension bridge, it is not built in strong windy regions. All right. And there are systems to dampen the vibrations as well. So my point is that, all this, whatever you learn here have a lot of applications in real life, engineering as well. Even in Japan, Japan has a lot of earthquakes every time, right? So they have a system to reduce the impact of earthquake on the building. All right, earthquake on the building. There are dampeners. There are huge balls suspended on top of the building. They'll carry the energy of vibrations. All right. Okay, I'll show you something anyway. Look at this. Let me see if I have it. Yeah, this is what, breaking glass with sound. So we have a glass here, and then a frequency is given from outside, sound frequency. It's like a time exposure camera so that you can see it vibrating, the glass vibrating. You can see the vibrations on the glass. With naked eye, you can't see. So it's kept against a speaker so that you can give sound from this side. Sound, when the sound frequency is changed, can you see it vibrating? Did you see that? Can you see it? The glass will eventually. That happens only at that particular frequency. It will shatter eventually, right? Okay, so this is the dampener I was talking about. Look at that. The building, and it's like an animation like this. Look at that. They suspend a ball on top of it so that it can carry the vibrations will be carried by the oscillations will be carried by the dampener. Look at that. See this. This has lesser vibration then, right? Than the other one. Or this one will tell you more. One second, let me see. Yeah. Breaking with voice. Just look at how much the glass will break. You just check it out on YouTube. There are many videos of people breaking it. It will shatter. Yeah. External frequency. And this is H. Please. You can see resonance happening here, no? Look at this. We have 3 oscillating systems, and all of them have different resonant frequencies. You can see them resonating at different frequencies. All right. This one will resonate, then this one will resonate, and this one will resonate at different frequencies. So you can see the frequencies given. Look at that. They start oscillating, right? Can't you see? So oscillating, right? Moving back and forth, right? Correct. The airplanes and all, no, they are subjected to these kind of tests. Otherwise, in turbulence, if it resonates, the wings will collapse. Okay. I'll just look at that. Starts oscillating faster. Now you can see one of them starting to vibrate vigorously. One of them. Who will hit natural resonance first? Let's see. Wait. Yeah, let's see. Just wait. So the frequency they are increasing. Frequency means number of vibrations per second. All right. That is resonating now, right? It is about to resonate. When resonance comes, there will be vigorous vibration. You can see it. Look at that. It's already resonating now. Look at that. Now, look at this. So 4 hertz. 4 hertz is the resonating frequency for this, which means 4 vibrations per second. All right. Now they keep increasing. See what happens? That will go out of resonance. This will come into resonance then at higher frequency. See it resonates at 4 hertz, right? Correct. But this has another natural frequency. You understand? My natural frequency is different from that of Abhinav's natural frequency. All right. So everything will have like a unique natural frequency. Now look at that. This starts vibrating, right? Frequency increases, right? So it will resonate at maybe like a bigger frequency, maybe like 10 hertz or something. Let's see where it vibrates. 6.35. Look at that. 6.35 vibrations per second. So when 6.35 hertz is the natural frequency, when the applied frequency, we have natural resonance for this. Now you keep increasing the frequency again. Okay. You keep increasing this up now. Look at that. You keep increasing the frequency. Look at this one now. The last one is resonating. Vibrating more. Faster vibration now. Okay. So it resonates at what speed? What frequency? Let's see. Oh. So that one was at 4. This one was at 6.35. And let's see where this is. Now they are not oscillating at all. So they are out of resonance now. That's what. 11.35. So the frequency is 11.35, which means it vibrates 11 times in a second. 11.35 times. This is the bridge collapse that I was. Please. The bridge collapse I was talking. Please. It's an actual bridge made of steel and concrete. Look at how it vibrates. See the vibration. It's an actual bridge. Suspension fiber.
In 35 miles an hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing.
It'll keep oscillating until resonance comes. Eventually it collapses at resonance frequency. Understood. And there was another one.